Welcome back, aspiring pilots and aviation enthusiasts. I'm stepping into the role of your flight instructor today for this digital ground school explainer. We are going to take all that complex data hiding in Section 5 of your pilot's information manual, the PIM, and decode it. We're turning those dry aircraft performance charts into intuitive, real-world flying knowledge.
We're structuring today's lesson exactly like a real cross-country flight. First up, speeds, stalls, and winds. Then we'll tackle takeoff and climb performance, followed by engine management and cruise. And finally, we'll bring it all home with range, endurance, and gliding.
All right, Section 1, speeds, stalls, and winds. Let's get our pre-flight planning locked in before we even touch the airplane.
So, starting off, take a look at the Airspeed System Calibration chart. This is basically your translation tool for converting indicated airspeed, the IAS you read directly off the dial, into calibrated airspeed, or CAS. Now, you might be asking, why do we even care about CAS? Well, getting your calibrated airspeed is an absolutely vital first step before you even think about grabbing that E6B flight computer. You actually need CAS to calculate your true airspeed, which is super important when you're planning for your top of climb.
But here is where it gets kind of fascinating. Different manufacturers treat this exact same chart completely differently. If you're flying a Piper Arrow, you go ahead and use this chart for your climbs. Pretty straightforward, right? But grab a Cessna PIM and you'll find a very specific warning note. Cessna actually restricts their charts strictly to level flight and descents. So how on earth do you find your climb speeds in a Cessna? Well, you actually don't use the chart at all. Instead, you have to whip out the E6B. Use the inner scale with your non-standard temperature to find true airspeed and the outer scale to get your indicated airspeed. The big takeaway here? Always read the fine print on your charts.
Moving on. This power-off stall speed versus angle of bank chart gives us some stark visual proof of a dynamic you absolutely must respect. Look at what happens as your angle of bank increases. Your stall speed shoots up dramatically. Why? It's all because of that extra load factor pushing down on the wings during a turn. It's basically a perfect reminder of why steep turns demand hyper-awareness of your airspeed.
Right before we fire up the engine, we've got to calculate our winds. And to do this quickly, without fumbling with mental math, you need the 5-7-9 rule of thumb. It is a lifesaver. It's elegantly simple. A wind angle of 50 degrees off the runway heading means your crosswind is roughly 30%. 70 degrees, that's 45%. And 90 degrees, a direct crosswind, gives you 60%. Burn this in your memory. It will save you an immense amount of time when you're busy in the cockpit. All right, Section 2, takeoff and climb performance. Our ground planning is totally solid, the engine's running, and we're ready to hit the skies.
So, here's a question I bet you've actually asked your own instructor at some point. Why do we continuously practice flap 25-degree takeoffs instead of just, sticking to a normal 0-degree flap setting?
The secret here is all about safety margins. Practicing with the flap set down at 25 degrees literally forces us to handle the worst-case condition on our performance charts. By mastering this specific setup, we're fully prepared and certified to take off safely on the absolute shortest, tightest runways out there. Basically, we train for the extremes so that your standard everyday flights feel like a breeze.
Okay, we're airborne. Now let's talk climb performance. If you're lucky enough to be flying a complex, retractable gear aircraft, the difference between your gear up and gear down climb charts comes down to one massive, undeniable factor: drag. Leaving that gear down creates a huge physical drag penalty. Aerodynamically speaking, as drag goes up, your available thrust physically goes down compared to what's required. A clean, gear-up climb eliminates that penalty completely, maximizing your thrust so you climb faster and much safer.
Now, when you're calculating your fuel, time, and distance to climb for that cross-country flight plan, there is one giant caveat you have to remember. The distance printed in the PIM chart assumes 0 wind. Never, ever just copy that number blindly. To find reality, you've got to follow 3 specific steps. First, grab your E6B and get your actual ground speed using the real wind conditions. Second, plug that ground speed in to find your time and distance on the flight computer. And third, well, there you go. You've arrived at your actual real-world climb distance.
Section 3, engine management and cruise. We've officially reached cruising altitude, so let's figure out how to squeeze every single drop of efficiency and performance out of that engine.
When you're setting your cruise power in something like a Piper Arrow, usually running at 2200 or maybe 2500 RPM, you absolutely have to factor in the outside temperature to get your manifold pressure, or MP, dialed in exactly right. Here's the trick. Use the 0.16 inches of manifold pressure per 10 degrees rule.
You add 0.16 if the temp is above standard, and you subtract it if it's below. So why do we do this? Well, it's simple physics. Warmer air is less dense, and when air density drops, your engine performance drops right along with it. So you physically have to push more manifold pressure into the engine just to get the exact same horsepower.
With your power set, you're faced with a strategic choice regarding your fuel mixture. Do you want speed or do you want savings? You can set the mixture for best power, which is literally designed to blast you to your destination as fast as possible. Or you can pull that mixture knob back to best economy. That's going to let you stretch your distance on the exact same tank of gas and, let's be honest, save a good chunk of change at the fuel pump.
To really master these settings, we've got to demystify EGT. That's exhaust gas temperature. In plain English, EGT is just the temperature of the exhaust shooting out of your engine's cylinders. As you slowly pull that mixture knob back to lean it out, you'll see the EGT gauge actively rise. This happens because you're feeding a lower ratio of fuel into the cylinder to mix and burn with the air.
Now, finding best power is practically a science. If you just keep leaning the mixture, the temperature hits a peak, and then surprisingly, it actually starts to drop because there just isn't enough fuel left to burn efficiently. That top point, that's your peak EGT, which basically means 100% of your fuel is being consumed. But here is the real instructor secret. Peak EGT does not actually give you your best power. No way. To get maximum power, you want to find that peak and then enrich the mixture by 100 degrees Fahrenheit, which is usually about 4 tick marks on the gauge. By enriching to peak EGT plus 100 degrees, sure, you burn a tiny bit more fuel, but you generate significantly more power.
Oh, and here's a really fantastic physics tip for your cruise performance. Your PIM gives you a calculated true airspeed that assumes you are flying at maximum gross weight. But if you're flying lighter than max weight, this beautiful chain reaction kicks in. Less weight means your wings don't have to work as hard, so they generate less lift. Less lift directly equals less induced drag. And with less drag holding the plane back, you're actually going to fly even faster than the true airspeed you originally calculated. How cool is that?
Section 4. Range, endurance, and gliding. Let's tackle the final phase of our flight, figuring out our remaining fuel, and diving into the vital physics of how to glide back down to Earth safely.
It's incredibly common for pilots to mix up range and endurance, but they are completely different beasts. Range measures the absolute distance you can cover, and fun fact, your range actually increases by about 1.5 nautical miles for every 10 degrees above standard temp. Why? Because that warmer air gives you a higher true airspeed. Also, range calculations always bake in a 45-minute safety reserve. Endurance, on the flip side, is purely about time, and here's the kicker. When you file your endurance on a flight plan, you calculate it with absolutely zero reserve. Zero. Why? Because if things go sideways, search and rescue teams need to know the exact minute your plane will mathematically fall out of the sky empty, so they know exactly where to start looking.
Now, heaven forbid you lose your engine in flight. Naturally, you pitch for your best glide speed, but suddenly you're faced with a really fascinating physics puzzle. Picture two identical airplanes. They both lose their engines at the exact same altitude. But one is loaded up to maximum gross weight and the other is practically empty. Which airplane has the greater rate of descent, meaning which one drops out of the sky faster? It might seem completely counterintuitive at first, but the heavier airplane will always have a greater rate of descent. It's simply going to hit the ground sooner than the lighter plane.
The reason behind this whole thing is gravity. Think about it, in a glide, you don't have engine thrust anymore. Your new thrust is actually just gravity. Specifically, it's the forward component of your aircraft's weight pulling you down the slope. So a heavier plane naturally wants to accelerate much more aggressively when pitched down. This increases its forward thrust, sure, but it also heavily increases its descent rate. On the flip side, if you pitch the nose up, you increase the rearward component of your weight. And that rearward weight, it acts exactly like a massive parachute of drag, rapidly slowing the airplane down.
Now, believe it or not, this exact same physics applies when you're climbing. The thrust you need to climb is way higher than in cruise because you are literally fighting that same rearward weight component. So I'm going to leave you with this. The next time you pitch up into a steep climb and you feel the engine roar and the aircraft really fighting to maintain speed, I want you to ask yourself, are you picturing that invisible rearward weight desperately trying to drag you right back down to the runway? Honestly, understanding these invisible forces, that's what separates a good pilot from a truly great one. Keep studying those charts, trust your performance data, and as always, fly safe.